And now, let's take a look at the program. After installing the program, you can see that there is TechWiz OLED and TechWiz OLED viewer. TechWiz OLED can create and manage the database and define the 1D structure and material properties for the simulation. TechWiz OLED Viewer allows the user to check and analyze the results by effective data processing. First of all, please double-click TechWiz OLED program. The following window appears. At first, it is main menu. Users can manage project files and set the options. Below that, it is toolbar. As shown, frequently used functions are displayed in the form of icons. And there are two types of modules: DB information, stack information, and condition. In DB information module, database creation and management are performed. After that, 1D structure definition and parameter setting of OLED devices can be processed in stack information and condition module. So from now on, let's take a look at the first module, DB information. DB information module consists of DB Explorer and information window. DB Explorer shows the DB files in the form of a list. In the information window, users can check and modify the property of the DB. The DB files are classified by type, and there are 3 types in total: material, layer, and light source. Material DB is the smallest unit. For example, if you double-click the PI, the property of PI is showed up in the information window. And the next one is layer DB. It is a convenience feature. By loading frequently used material DB and setting the additional properties such as an optical axis and thickness, it can be much easier to define a multi-layered stack structure. As an example, please double-click single SMPL. In the material term, there is a saved path. It is uni SMPL, which is a uniaxial material DB is loaded. Based on this material DB, various parameter settings such as thickness and optical axis are showed up. Lastly, light source DB. It is used for the external light source or the emitter of a layer. Additionally, there are some icons here. Users can search the particular DB or create a new DB file by clicking this new button. Also, users can delete the DB file. First, click the particular DB and click this delete button. But there are 2 ways to remove it. If you click remove, the selected DB file is removed in DB Explorer list. And if you click this delete button, it is permanently deleted. So far, a brief description of the DB information module has been completed. If so, let's see how to create or check the DB file according to the DB type. Please click the New button. When creating a new DB, first define the name, saved path, and select the DB type. The first thing that I will check is material DB. There are 6 detailed DB types: isotropic, uniaxial, biaxial, metal, color filter, and polarizer. So let's look at the example starting with isotropic. Isotropic material means that the optical properties are the same in all directions. I will enter the name as ISOEX and use the default saved path. Click OK. Defined DB name appears. You can also modify the name. If you want to, you can enter some descriptions of the DB file. And there is only one tab, refractive indices. Set the refractive index of the DB, and it should be defined as real part and imaginary part separately. Let's see real part first. There are 3 types of methods: constant, coefficient, and wavelengths. Choose the method and enter the information. After that, by clicking the Make Table button, the calculated refractive index data is showed up in this table. Currently, it is set as default value. The wavelength is set to 550 nanometers, and refractive index is 1.5. As such, if the refractive index is defined for one wavelength, it means that the refractive index is the same for all wavelengths. For example, I will select constant and enter 1.7. However, in the table, the refractive index does not change. Unless you click the Make Table button, the refractive index value does not change. Therefore, after entering the value, please remember that clicking the Make Table button is the most important thing. And if you want to define the refractive index for a wavelength range, select the step from the list. For example, I will select 20 nanometer step. After that, if you press the Make Table button, the refractive index value set in constant is supplied to the all refractive index values for the wavelength range. You can modify the particular refractive index, or also you can modify wavelengths as well. If you want to delete the data, drag the area and then click Delete button. For additional options, please utilize these icons above. Also, the table data is compatible with Excel spreadsheet, so it is possible to copy and paste the data. The next one is coefficient. There are 4 types of equations. Select the equation and enter the coefficients. As an example, I will select Selmayr 1 and enter like this. And then set the wavelength step as 20 nanometer step. And then click Make Table button. Based on the information, refractive index values for each wavelength are automatically calculated. Right now, wavelength range is applied from 380 to 780 nanometers. If you check Use the extended wavelength range, you can define refractive indices for the range from 200 to 2000 nanometers. So click OK button. And then select the wavelength step again. You can see that the wavelength range is changed from 200 to 2000. So you can utilize this option as well. Lastly, wavelength method, which obtains the refractive index for all wavelengths by entering only a few refractive indices. For example, I will enter like this. And click Make Table button. Select the fitting equation and then enter the values. I will use the default, so click OK button. As a result, refractive index values for each wavelength are automatically calculated. Let's move on to the imaginary part, which is relevant to the absorption properties of the material. The methods are quite similar to the real part setting. However, there is a precaution. In the real part, we already defined all refractive indices according to the wavelengths. So when defining the imaginary part, please note that you should not click the wavelength step. If so, the refractive index of real part information disappears. Therefore, enter the information and just click the Make Table button without additional selecting wavelength step. For example, I will select constant and enter 0.5 and then click Make Table button. It can be seen that the information of the real part remains as it is and the imaginary part is set for all wavelengths range. The next one is coefficient. There is only one equation, exponential. As an example, I will enter like this. And then click Make Table button. Based on the information, imaginary parts are automatically calculated. The following one is wavelengths. It is also the same as the real part. For example, I will enter like this. And then click Make Table button. Select the fitting equation, and there is only one equation, exponential, and enter the values. I will use the default. Click OK button. As a result, automatically calculated data appears. In the imaginary part, there is an additional method, transmittance. Let's take a look at the slides and go through each option in detail. Transmittance measured is used when users don't have any information about the imaginary part, but measured transmittance data is available. At first, please enter the thickness when transmittance was measured. When it is default, only the result of measurement with the material, that is, the surface reflection of the material. Uniaxial material is that the refractive index of one axis is different from the other two axes. So in this case, additional extraordinary axis should be set. Let's go back to the program and please click this new button. As the same way, for the DB type, I will select uniaxial and I will define the name as UniEX and use the default saved path, and then click OK button. Just like isotropic, there is only one tab, refractive indices. They look similar, but there are some differences. At first, let's start with the rear part. As I mentioned before, there is an extraordinary axis item. You can choose between X and Z axis. In TechWiz OLED, the reference axis is always the extraordinary axis, that is the NE direction. As shown in the following figure, if the extraordinary is set to x-axis, NE is applied based on this axis. In the same way, this figure shows when the extraordinary is set to z-axis. In this example, I will set the extraordinary axis as x-axis. And there are three types: constant, coefficient, and wavelengths, like isotropy. And the setting method is also the same. However, the only difference is that you should enter two refractive index values, NE and NO. I will show you only one example by using wavelengths method. Click this Insert Tab icons and enter values. And then select Wavelengths step. After that, click this Make Table button. Choose the fitting function and then enter the coefficients. I will use the default values. Click OK. The refractive indices will be automatically calculated as follows. Let's move on to the imaginary part. The imaginary part also looks the same as isotropic, except that you should enter KE and KO. But there is one more difference in transmittance measured. Additionally, select the transmittance measurement method. Since TS, TP, and TC are divided into two types, depending on whether the absorption axis is extraordinary or ordinary. Therefore, there are mainly TE, TO, and TS, TP, TC methods. It is relative to the method of measured transmittance. Let's see TE and TO first. Select when entering the transmittance measured in the extraordinary and ordinary axis. And TS, TC, TP stand for single, crossed, and parallel respectively. Therefore, you can choose the transmittance measurement method that suits your situation. And I will simply use constant to give an example. After entering KE and KO values, you should click this Make Table button without selecting this wavelength step. So you can see that KE and KO values are showed up. And please click the Save button. The next one is biaxial. Since biaxial means a material with three distinct optical axes, the refractive indices for the three axes should be defined. So, please click this new button and let's check biaxial. I will define the name as BiEx and use the default saved path. Click OK. As you can see, there is only one tab, refractive indices. And it is the same as isotropic material, except that you should enter NX, NY, and NZ values. Similarly, if you click the imaginary part, the settings are the same, so I will skip how to define it. Since all three axes are different, there is no way to inversely calculate Kx, Ky, Kz by entering the transmittance. Therefore, the transmittance method does not exist for the biaxial material. And the next DB is matter. Please click this new button and click matter. And I will define the name as Metal EX and use the default saved path and then click OK. You can see that the refractive indices tab is the same as isotropic, so I will skip it. But there is another tab, reflectivity. In the reflectivity tab, users can directly input the reflectivity according to the wavelengths. Enter the reflectivity between 0 and 1. The values are applied as it is without any calculations, considering the reflective index with the interface layers. For example, If the reflectivity is 0, the incident light is totally absorbed. Moreover, if you input 0.5, it means that the reflection rate is 50% and the extinction rate is also 50%. So just click this Insert Tab button. You can enter the wavelengths and reflectivity. So far, we have identified isotropic, uniaxial, biaxial, and matter properties. In the material dB, a color filter and a polarizer are left, but they are exactly the same as the dBs that we checked before. So instead of creating a new dB, just simply check them by clicking already created dBs. So for the color filter, please double click this dB. As you can see, it is the same as isotropic material. But please remember that the definition of the imaginary part is very important for the color filter. And the last material dB is a polarizer. Please double-click this polarizer. As you can see, it is the same as a uniaxial material. So please refer to the uniaxial part. So this is the end of the material dB. And let's move on to the next dB type, layer dB. Actually, you can define the properties of each layer when stacking layers in the Stack Information and Condition module. But it will be more convenient to predefine the frequently used layer dB in the dB information module. However, since it is a convenience, not a necessary thing, there is no need to define it unconditionally. So if you click this new button, there is a layer dB type, and there are 3 types of layer dB: single layer, group layer, and exoscan layer. Let's check each one step by step. The first one is a single layer. The single layer is composed of one material. Let's simply check how to create a new single layer dB. I will enter the name as single EX and use the default saved path. Click OK. So the first thing to do is loading the material dB that you want to make into the layer dB. As an example, I will drag and drop this uni SMPL. The saved path of this material dB is showed up. Also, name, type, and extraordinary axis information appears. And you can set the thickness and the number of division. For example, let's enter 5 for the division. The number of loads changes according to the division values. When the optical axis is homogeneous, it doesn't matter what the division value is. However, if you select inhomogeneous function or inhomogeneous table, the division value affects the calculation. So, 3 or more than that should be entered. For the calculation accuracy, 21 is recommended. You can see that this part is just for the uniaxial and biaxial only. So, if the loaded material dB is uniaxial, please define theta and phi angles. And if it is biaxial, input theta, phi, and psi angles. And there are 3 types: homogeneous, inhomogeneous function, and inhomogeneous table. Homogeneous is selected when the optical axis is homogeneous of the single layer. So it means that the optical axis is homogeneous from top to bottom surfaces. On the other hand, inhomogeneous is that the optical axis is inhomogeneous. Let's start with function. Function inputs the angle from the top to bottom, and the bulk region between them is set by the gamma values. It can be checked in real time with graph and 3D model. As an example, I will enter the theta angle for the top part as 90 degrees. You can see that the graph and 3D model are changed. After that, if you click this Make Table button, you can check the angle values in each area according to the division. And if you click this inhomogeneous table, you can directly input the angle information or paste it Excel or Notepad. The next tab is two-axis analysis. It looks complicated, but it is the same as the screen shown on the ExoScan measuring device. Since values are calculated based on the data set in the Layer tab, you can check the characteristics. The meaning of each item is written in the manual and tutorial, so please refer to the documents. In the Decomposition tab, data can be checked in the form of a Mueller matrix. Finally, in the Multi-Domain Analysis tab, the data is displayed only when the multi-domain function is applied in the group layer. So for this part, let's check it out later on. And the next layer DB is a group layer. The group layer will be briefly explained through some slides. Depending on the type, different types of group layers can be created. Stacked, multi-domain, color filter RGB, and color filter RGBW. For example, let's suppose that I made 4 single layers. And if I choose stacked, 4 single layers are stacked along the Z-axis. In the case of multi-domain, for single layers, make a multi-domain group layer. For the color filter layer, there are two types, RGB and RGBW. If you click this new button, this window appears. First, please select the DB type as group layer and then define the name and folder. After that, click OK button. Let's check the stacked group layer first. Drag and drop the layers from Material DB or Layer DB. And then you can change the position of a layer or delete a layer by using these icons at the bottom. A stacked group layer is created as shown in the following figure. Next is multi-domain. Additionally, the ratio term is activated. You can enter the area ratio for each domain. For example, if you enter 1 for each domain, the following multi-domain layer is created. Additionally, for the multi-domain group layer, you can check the data for each domain in the multi-domain analysis tab. Also, you can make a multi-domain layer using stack group layers. The next one is a color filter. In this case, you can set the ratio and CFID. For accurate color calculation, the CFID for each color filter should be clearly set. A color filter RGBW can be also created like color filter RGB. Also, there is CFID too, so users have to define the CFID for the color filter. Next is the ExoScan layer. As an example, please double-click Exo SMPL. It is to create a layer using the Miller matrix data measured with the ExoScan device. Click this Add button to add a Miller matrix data file. You can check the extension of the ExoScan data file. So choose the file and then click this Open button. And then enter measurement conditions such as wavelengths, theta, and phi values. After that, click the Save button. The other tabs are the same as a single layer, so I will skip them. In this way, I have explained all the contents of the Layer DB. The next one is Light Source DB. In TechWiz OLED, there are three types of light sources: external top, external bottom, and the emitter of the layer. You can set the spectrum data according to the viewing angles and wavelengths. And based on the spectrum data, you can also check the luminance. As an example, please double-click this red light source. When uniform viewing angle type is checked, theta and phi items are disabled. Therefore, it means that it is a Lambertian light source with the same spectrum data for all viewing angles. If you click the Spectrum tab, you can see that there is no list for the theta and phi angles to select. Since it is a Lambertian light source, just set the spectrum data according to the wavelengths, and the graph is showed up. Based on the spectrum data, you can also check the luminance. And as an example of non-Lambertian light source, please double-click Light Source SMPL. In this case, Uniform Viewing Angle type is unchecked. Also, theta and phi step are enabled. You can input spectrum data values according to the viewing angle interval. If you click the Spectrum tab, you can see that there are lists for the theta and phi angles, and also there is information according to the viewing angle. And based on the spectrum data, the luminance data is automatically calculated. You can check the low data in the data table. So, we have discussed the method how to create and manage DB materials. This is the end of DB information module.